We present RoboNet, large-scale multi-robot learning. We hypothesize that in order for robot learning algorithms to generalize across a large range of environments, they must be trained on substantially larger and more diverse training sets. Inspired by the breadth of the ImageNet dataset, we introduce RoboNet, a dataset containing roughly 150,000 trajectories with video and action sequences recorded from 7 robots, interacting with hundreds of objects with varied viewpoints and environments corresponding to 15 million video frames. The data is collected via a randomized collection policy designed to lead to object interaction and grasping. Since data collection is unattended, large amounts can be collected cheaply. Collecting this data across 4 different institutions allows us to naturally induce diversity across robots, grippers, tabletops, objects, viewpoints, and lighting conditions. Having collected this dataset, we study how models trained on RoboNet can enable generalization across viewpoints, grippers, and robots. In our experiments, we study generalization for both model-based reinforcement learning and inverse models trained with supervised learning. We use the Visual Foresight model-based reinforcement learning algorithm, which leverages an action-conditioned video prediction model to plan actions towards user-specified goals. To plan, we sample a large number of action sequences and apply the best action sequence to the robot. We first study zero-shot generalization to new viewpoints, which is challenging because the video prediction model has to identify the relative position and orientation of the camera to the robot-based coordinate frame from a sequence of context images passed to the RNN. We compare a model that was trained on 90 different viewpoints with a model that was only trained on a single viewpoint. In this video, you can see the robot successfully executing a pushing task from a held-out viewpoint using the multi-view model. On the bottom left, you can see the predictions for the best 3 action sequences found. In our experiments, the multi-view model performs significantly better in terms of object positioning accuracy than a model trained on a single viewpoint. It is extremely challenging to generalize to new environments with a held-out robot. That's because the algorithm must adapt to unseen experimental conditions, like new backgrounds, camera viewpoints, and lighting conditions, as well as a new robot, with different visual appearance and physics. We pre-train a model on all of RoboNet but Baxter's, and then fine-tune the model on 300 trajectories collected from a new Baxter robot. The final model can be used for control. In this case, the robot wipes a table with the towel. We compared performance on 10 different object relocation tasks, and find that a model only pre-trained on Sawyer robots has the best performance. We hypothesize that this is due to the high degree of visual similarity between a Sawyer and a Baxter robot. We show that RoboNet fine-tuning works for different robots too. In this case, the Franca Pandas robot moves the bottle next to the erasers. When pre-training on all the RoboNet data and fine-tuning on just 300 trajectories from a Franca robot, performance is better than training models from scratch on 8,000 trajectories from a Franca robot. The first 2 table rows show control performance when using the models trained from scratch, and the last shows the pre-trained model's performance. Note that R3 and Fetch robots were excluded during pre-training due to computational constraints. We're also able to use fine-tuning on RoboNet to control a KUKA robot. Here, the arm can push a cup along the marked line. When fine-tuning a model pre-trained on all of the RoboNet data except from the KUKA robot, we achieved significantly higher performance than a model trained only on the KUKA data. Note that R3 and Fetch are again not included during pre-training due to computational constraints. In addition to visual foresight, we demonstrate that a simple self-supervised inverse model can be trained on RoboNet to perform control. Here we demonstrate the completion of a successful reaching task. During our control experiments, we noticed that the trained visual dynamics models were heavily underfitting. This motivated us to study how much model size affects prediction performance. We find that even massive models, with 500 million parameters, underfit on RoboNet, although they clearly perform better than their smaller counterparts. Thus, training good visual dynamics models on RoboNet is an open challenge.